Hello, everyone. Um, Welcome to our fourth lecture in ECE 560, Modern Control Theory. I hope everybody is keeping warm. Today um, we've switched to completely online mode. So before we get started, do you have any questions regarding the previous material? All right, so we've seen several things up till now. We've seen state space models, we've seen transfer functions, we saw how to solve linear systems, and how to convert between state space and transfer functions and things of that sort. So today we are going to extend it a little bit. And also introduce the idea of controllability in state space. So the first thing I would want to talk about is really the non-uniqueness of state space models. So I remember we've said it before that state space representations are not unique. Right, so state space in general but the transfer function is unique. Okay, so if you have a certain system or certain control system, you will always have a unique transfer function, but it can result in infinitely many state space representation. So we'll see why that happens, and can we convert from one state space representation to another. So the transfer function okay, so the key idea here is a similarity transformation in state space. Which means can we transform a state space model into another state space model, which is an equivalent system in terms of its response. And when I talk about response, I really mean the poles and zeros of the system are the same. Okay, so let's consider a state space model. Like always, the standard x dot equals ax plus bu, and we want to transform this system into a new system. So we'll see if you do a linear transformation, then there's many transformations that are possible, but it is essentially the same system, and we will prove that in a while. So starting from the standard model, x dot equals ax plus bu and y equals cx plus du, we can actually define another state space. And that's going to be a non-singular and when I say non-singular, that essentially means the transformation matrix that we use is invertible. So a non-singular transformation matrix we also refer refer this matrix as the similarity transformation matrix, as a similarity transformation, and this transformation is called x bar equals to tx. Okay, so we have a new set of state vector, and that's some matrix T times the vector, old vector X, right? So this is kind of the new state vector, right? This is the transformation matrix, right? And this X is the old state vector. So if you have this representation that transforms the original state vector to a new state vector, so you are actually going into a new state space, and we want to see whether the state space dynamics can also be transformed into a new state space model with matrices A bar, B bar, C bar, and D bar. Okay, so from here, one thing you can directly see is that if you try to isolate X, then you will have X equals to T inverse X bar. So this is only possible if T is invertible, and that's why we want to have a non-singular transformation when we transform our state space models. Okay, so our transformed state space will be the new set of dynamics and a new output equation. Transformed state space model can be written as this new X bar dot equals a something X bar plus something U, and then Y. The output is again a function of X bar and U, but the matrices now will be different. So we'll have A bar, B bar here, C bar, and D bar. Okay, so we'll see how we can derive what the A bar is, what the B bar is, what's the C bar, what's the D bar. Okay, and we have to start from our definition of the transformation. So we defined our transformation X bar to be T times X, which is the old X. So let's start the derivation. So we said X bar dot is actually the derivative of Tx, right? So Tx is the matrix, and then the dot is over it, right? But the T is a constant matrix, so it's actually Tx x dot, right? Because T is a matrix of constants, which is transforming our old state into a new state. Then if you take the time derivative, then it's only applicable on the X. Okay, so if you have this, then by definition of the old system, X dot equals to AX plus BU. So we will have T times AX plus BU, right? So we have X bar dot equals to T AX plus TBU. For the new model, we want x bar dot as a function of x bar, right? So we'll have to replace this x here. So we'll say this x is actually t inverse x bar. So so this gives you the state equation x bar dot equals to t a t inverse x bar plus t b u. So by comparison, basically this thing here can be the a bar, and this thing here is the new matrix b bar. And similarly, if you go back to the output equation, which is y equals to cx plus du, you can use the same trick here to replace the x with the x bar. So we'll have c t inverse x bar plus du. So the output equation will be y is c t inverse x bar plus du. So again, by comparison, this here is the matrix C bar, this is the matrix D bar. Okay, so I'll write a summary of the transformation of a LTI system using a similarity transformation. So let's summarize everything. So I said if you have an original system which is x dot equals to ax plus bu, and then you have a matrix y is cx plus du. And if this goes through a transformation where x bar is dx, then the new system becomes x bar dot equals to a bar x bar plus b bar u, and y equals to c bar x bar plus d bar u. And if this is the case, then where a bar will be t times a times t inverse, the b bar is t times b, the c bar equals to c times t inverse, and the d bar equals to d. So that's a summary of the similarity transformation of the LTI system. Okay, so from here, you can see that there's infinite many possibilities for you to pick T, the transformation matrix. So in other words, you will have infinitely many different state space models that represent the same system. So to prove that, let's look at what is the transfer function of the transformed system. And that will really prove to you that there is really no difference in the original state space and the current state space. So transformed, or maybe let's say transfer function, the transformed system. Okay, so the transfer function, if you remember, is you can use the matrices in the linear control system equations to compute the transfer function, and I'm going to write that expression here. So the transfer function will be the matrices C times Si minus A inverse times B plus D, which we presented perhaps in the second lecture. So transfer function of the transformed system is, let's call G bar of S, which is C bar times Si minus A bar inverse B bar plus D bar. Okay, and here we can replace the matrices in terms of the original matrices to see what happens. So the C bar from the definition here is going to be C times T inverse. So let's write C times T inverse here. And the rest is as it is, minus A will be, A bar will be TA T inverse. So we're just going to replace these new matrices in terms of the old ones. So B bar here was T times B, right? And then D bar is the same as D. So we'll use the same expression here. So let's expand it here a little bit. So now this is going to be C times T inverse. And so we'll do a little bit of manipulation here. So let's try to write T I T inverse, and then let's use the S here. Right, S is a scalar, so it doesn't matter. And you just introduce T and T inverse, which cancels out, but it's going to play an important role at in simplifying this expression. So minus TA T inverse, and then there's a whole inverse outside times TB plus D. So now what we can do is we take T common. So inside we will have Si and then minus A, and let's put T inverse outside. Okay, and then the rest just follows as it is. And now we will expand this. So so if you take the inverse of this matrix, or of this product in the middle, basically you will have to inverse the internal elements and then reverse the order. So for example, I mean, A, B, C inverse is actually C inverse, B inverse, A inverse. So we use this property here, and that's going to be, so this thing here is going to get inversed and come here. So that's T here. And then the next one is Si minus A inverse, and then T inverse. Next is T and B plus D. So you can see what is happening here is that this is identity. This here is identity. And what you're left with is C times SI minus A inverse B plus D, right? Which is by definition the transfer function of the original state space model. So therefore, what we can conclude here is that transfer function does not change when under a linear transformation of the state space. Right, so you can see that a system will have a unique transfer function, but it can have many different state space representations, depending on what is the matrix T that you're using. Under linear transformation of the state space. Okay, so that was the first part that we wanted to talk about today. And the next thing really is the controllability of a linear control system. So I know we have talked about it, but let's do it more formally today and provide a way to test whether a system is controllable or not, because controllability is important in order to have a reason to design a controller. If the system is not controllable, then the input U is not going to do anything. So you may not be able to steer the system to wherever you want. So controllability of a linear control system. So formally, the controllability concerns or determines whether we can steer the system to anywhere you want. So determines whether we can steer the system or the state, basically steer the state of the system via the control input to certain locations in the state space. So controllability will have many sort of categories, and most oftenly when we say controllable, we really mean a system that is completely controllable. So just want to make it clear that complete controllability will mean that you can steer the system anywhere you want, right? So it's not only a set of states or a set of locations that you can steer the system into, but it's really everywhere. So formally, we can say that if for any initial state x0, and that's also important. So wherever you start the system from, it shouldn't really matter. If the system is completely controllable, you should be able to steer the system anywhere. So for any initial state x0 and any final state xf, or let's call it x1, there exists an input u of t that transfers x0 to x1 in a finite time t. Right, if this is the case, then the system is completely controllable. Okay, so in other words, it means that in a state space, like let's say this is the sort of possible states, then you pick any x0 and you can pick any x1, and there will be a input that will take you from here to there. So maybe it could take different routes, but this is one possibility, but this is the other one, and so on. So the point here is you can pick any x0, any x1, and some input will take you there. So that's the definition of a system which is completely controllable, and hence there is a point in thinking about what that input is, right? And whether we can design a control input that can take you there in a minimum effort or minimum energy consumption, or so many other design vectors. Now, the question is, how do we know if the system is controllable? Right, if that's the definition of controllability, by looking at the state space system or state space representation of a system, how can we determine whether the system is completely controllable or controllable? So there's several ways people have been using to determine controllability, and some of them are related to the frequency domain analysis, which we are not going to talk about. So we are only going to be focusing on state space models, which means that you are in the x dot equals to ax plus bu domain, and from there you want to determine the controllability properties of the system. So here I'm going to give you a key result. It can actually be derived, but I'm not going to do the whole proof here, but I'm going to give you the key result. So consider a system derived by x dot equals to ax plus bu and y equals to cx plus du. Then the controllability only depends on the matrices A and B. So this is fact number one. So controllability only so A and B, right? Which is kind of intuitive because the state is being evolving here, right? So whatever input you provide, the state evolves according to this. So really this equation should be the only one concerning whether the system is controllable or not. Okay, so how do we do it? If we just look at the state equation, we will have to construct a controllability matrix. So the controllability of the LTI system is determined using the controllability matrix, which is defined in a special way. So controllability matrix, and let's call this matrix C of A, B. Right, so it's a function of the matrices A and B, and it's defined as is defined as the augmented set of vectors where you will have first the vector B, and then you augment so you are trying to attach a set of vectors together and form a matrix. So the first column of that matrix is the vector B, then you attach A times B, and then you attach A squared B, right, and A cubed B, and so on until you reach the maximum limit, which is A times n minus 1B, right, where n is the number of states. So let me also write that here. Okay, so you have to construct a matrix which comprises of these vectors, and the system is controllable if this matrix is invertible, right? Or in other words, it is full rank. So system is controllable if CAB is invertible. Right, and in other words, if CAB is full rank. Right, the condition for invertibility is that the matrix has to have full rank. Yeah, I mean, this C should be a little different because it's not the matrix C, it is the controllability matrix. And it is a function of the matrices A and B. Okay, so let's do a small example to get us started with how to determine whether a system is controllable or not. So let's do a state space system, and you need to determine the controllability property. So for an LTI system described below, determine whether it is controllable. So the The state space model is given by x1 dot, x2 dot, x3 dot equals 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6, x1, x2, x3, plus 0, 1, minus 3, u. Okay, so that's the system, and mind you that the other equation doesn't really matter, right? So right, so it's y is some x plus some u, right? So this equation doesn't matter for controllability. Okay, so just from the theorem that we just stated about determining controllability, we have to construct the controllability matrix. So that's the first step that we should take. CAB okay, so CAB is going to be B, remember AB, and A n minus 1B. So n is 3 here, so we stop at A squared B. Right, so I mean, this is an imaginary line here. So we will not have A cubed B because we only have 3 states. So we start with the vector B, then A times B, and then A squared B, and which is already the A to the power n minus 1B. So the first vector, which is B, is already available in the system. So you already know what this is. It's coming from the system. So it's 0, 1, and minus 3. The second vector is A times B. So let's try to compute this. So this is the matrix A, which is 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6 times the vector B, which is 0, 1, minus 3. So this is going to be the first entry is simply going to be a 1, but if you multiply this, you will get this entry. The second entry is going to be a minus 3. And then the last entry is minus 11 plus 18, which is a 7. So that's A times B. Now the third column vector is A squared B, which is actually A times AB. And you already have computed the vector AB. So, I mean, that's the way to go. Instead of starting from the beginning and multiplying A twice and then multiplying by B, you can just pre-multiply the AB with the matrix A again. So the A is 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6, And then AB, we have already computed 1 minus 3, 7. So this will turn out to be minus 3, 7, and 15. Okay, so we've got this. Now, the next step is to put it together into the controllability matrix. So what we will get is 0, 1, minus 3, 1, minus 3, 7, minus 3, 7, 15. Okay, so this is our controllability matrix C of A and B. So the question is whether this is invertible or not, right? So one way is to see what is the rank of this matrix. So rank will there's several ways to do it. If it was a smaller matrix like a 2 by 2, I would go take the determinant route. Here also you can actually do a determinant computation. But what I will do here is to reduce this matrix using row elimination, and then try to see what is the rank. It's like a very basic way of doing it, but you can take any method you like to see whether the matrix is full rank or not. And as I told you, the one way is to see if the determinant exists. If the determinant exists, then definitely it's an invertible matrix.
Professor, is that a negative 15?
Oh yes. Yeah, it should be a negative 15.
That's a negative 14, I guess, Professor.
No, so minus 6 plus 33 plus 42. So 6 and
minus 42.
Yeah, so minus 42 and then 33, which is what? Minus 9, right? And minus 6, which so it should be minus 15.
Oh yeah, sorry, Professor. Yeah, it's minus 15.
Yeah, thank you for pointing this out. So I'm going to try to reduce this using Gaussian elimination. And this elimination method is really a way to try to see whether one vector can be represented as a multiple of the other one or not. So let's try to do it. The matrix is 0, 1, minus 3, 1, minus 3, 7, minus 3, 7, minus 15. Okay, so first thing is to try to knock out the last row. So I'm going to use an operation. So if you do 1/3 of row 3 and you add it to row 2, then you get you actually knock out one of the terminal number. So the first 2 rows will be as it is. Here you will get 0, minus 2 over 3, and 2. Okay, so So what we will do next is,
Professor, can you explain what is the purpose of doing the row elimination?
yeah, row elimination is, so we're trying to convert the matrix into a triangular matrix. So for example, I mean, if there's a matrix where you have some number here, right, and the zeros here, then I have like 3 pivot elements and the rank is 3. But if I get a 0 here, then the rank is 2. So it's really basic linear algebra. If you want to determine the rank, there are several ways, but one of the ways is called the Gaussian elimination method. And if you read about it, it's what you do is you try to eliminate rows. Okay, you can read about it also, and if you still have issues, you can contact me. Okay, now this matrix, what we will do here is, because there's a this number here, so we will try to exchange the rows and get it on the top. Right, so exchange rows. So these are all linear operations that you can do in a matrix. So the first row will be 1 minus 3 7 0 1 minus 3 0 minus 2 over 3 and 2. And then now we want to eliminate this guy here. Right, so in order to do this, what we will do is we will do 3 over 2 times row 3 plus row 2. So 3 over 2 will make it 1, and minus 1 actually, and then if you add it to the second row, this will get zeroed out. So the next step will be a matrix 1 minus 3 7. So 0 1 minus 3 here 0, this will become 0, and then minus 3 plus 3 will also get 0. So what you see is we only have 2 pivotal elements or pivotal entries. So therefore the matrix only has rank 2. So the controllability matrix has rank 2, which is less than 3, right? Which is less than n, which is 3. So n actually is the number of states. So if your rank falls below the number of states, then you can say that the system is not completely controllable. Right? However, partially it might be. So we'll see how we can further split up the system into a controllable part and an uncontrollable part. But for now, if you ask me if the system is controllable, meaning fully controllable, I will say it is not. So the system is not controllable. Right, so just by looking at this state space model, I can tell you cannot steer it anywhere you want. You cannot make the state go from x0 to any x1 you like, because there is one state at least which you cannot control. So since CAB is not full rank, Okay, so this was an introduction of controllability. We saw the formula, we saw the controllability matrix and how to go to its rank and then see whether it is full rank or not. And the next thing we will study is how do we convert a system into a controller canonical form. So there's a new idea called a canonical form of a control system, which can either be a controller specific form or an observer specific form. So we'll see next time, but what observers are. But today we are going to start with a controller canonical form. So let's go back one step and see how did we get to the state space model from the transfer function. So from transfer functions to state space. So let's start with a very generic transfer function. Given a g of s. So if we had a transfer function g of s, which we defined as the y of s divided by u of s, it's really in the form of a fraction, and you have polynomials. So you have a polynomial function of s in both numerator and the denominator, and we said that the roots are poles and zeros, poles being the roots of the denominator and zeros are the roots of the numerator polynomial. So if I just want to write the polynomial in a generic way, let's say it's going to be a I is 1 to n, bi minus 1, si minus 1. Right, so it's a polynomial of degree n minus 1 on the top, and in the bottom there is a polynomial of degree n. So you have s to the power n plus I is 1 to n, ai minus 1, s to the power I minus 1. Right, so this is a very generic form, and you can express any system in this form. So for example, if n equals to 3, then you will have, generically speaking, a transfer function, which is b2s squared plus b1s plus b0 divided by s cubed plus a2 s squared plus a1s plus a0. Right, so I'm writing it in a very generic way with constants a0, a1, a2, and b0, b1, bs. Now there's a way to convert this directly into state space in a form that's called the controller canonical form. So let's see what that is. So the controller canonical form. So its canonical form means a representation, a certain way to express a. It's one of the possible forms of writing that control system, but it's inspired from the controller design aspect, so that's why we call it a controller canonical form. So it can be expressed using the following matrices. So the matrix A can be written as 0, 1, zeros all the way. So the matrix A will be like this diagonal above the principal diagonal is all ones. And the rest are all zeros. Right? And the last row is an interesting the last row is pretty interesting because it's minus A0 minus A1 and all the way to minus A and minus 1. Right, so that's really the coefficients of the denominator in the transfer function. Right, so if you look at the transfer function and the denominator A0, A1, A2, A3, and so on, if you reverse them with a negative sign, those will be the last row of the state space representation in controller canonical form. And the matrix or the vector B is going to be 0 and all zeros except the last element, which is 1. So I will write here, these are coefficients of denominator of our denominator polynomial. Reverse that's negative sign, right? And the vector C or the row vector C is actually B0, B1, B2, all the way up to Bn minus 1. Right, so let me also highlight this. And these are the coefficients of the numerator polynomial. And the D vector of D is going to be 0. Okay, so this is a way to convert a transfer function into state space directly into a controller canonical form. And controller canonical form is special because of the way it is constructed. So the denominator polynomial coefficients, if you reverse them and negate them, they become the last row of the matrix A, and the other parts are standard. That means you will have ones on the diagonal above this, and the rest elements are zeros. B is in a standard way. The matrix C is constructed as using the coefficients of the numerator. So if you had any transfer function, you could go to state space directly into this form. And this is again one valid form of the LTI system, as we saw in our lecture, in the beginning of the lecture today, because you could transform any system into any other system using some transformation. So obviously, if your state space was different, you could transform it into a controller canonical form. Okay, so let's do an example to actually illustrate this further. So I'm going to write a quick comment here that any completely controllable system can be expressed in the controller canonical form. Okay, so now the example. So example is just to demonstrate that a system, if it is controllable and has a transfer function representation, then you can directly write the controller canonical form. So converting a controllable system to controllable canonical form. So we consider a system where the matrices A as -15, -15, 8, 7, and the vector B is 1, 1. And as I said earlier, C and D doesn't matter, right? So whatever C and D is, do not play a role. Okay, so first thing is to see whether the system is controllable or not, before even thinking about a controller canonical form. System is controllable. Okay, so how do we check it? We construct the controllability matrix CAB, and which is the augmentation of B with AB. So the vector B is 1, 1, which is directly obtained, and A times B is minus 15 plus 8 is minus 7, and minus 15 plus 7 is minus 8. So that's your controllability matrix. Again, you know, so any method to determine the rank. I mean, this time I will use the determinant, right? Well, let's what is determinant? So it's minus 8 minus. It's actually 1 over minus 8 minus, the determinant is simply minus 7, so it is going to be minus 1, right? So since determinant is non-zero, CAB is a full rank, right? So therefore, system is controllable. So that's good that the system is controllable. Now, next step is to see how we can convert it into a controller canonical form. So controller canonical form, if you remember, is A bar will be 0 and 1, and here we have minus A0 minus A1, right? Because it's a two-state system, so the A bar is just 2 by 2. The B is all zeros except the last entry, so it's going to be 0 and 1. B bar here. Right, and note that, you know, note that both A, B, and A bar, B bar have the same transfer function. Okay, so that means if I were to compute the transfer functions, it was C SI minus A inverse B plus D. This should be equal to C bar SI minus A bar inverse. Can everybody mute yourself if you're not speaking? There's some echo going on. So we didn't have any C and D. So actually, if you had this system, you know, you could actually just cancel out all the extra stuff. So C can go away. Well, I mean, it's not the right way to do it. Actually, the better way to I mean, it is true, it will cancel, but not directly. You have to substitute something. So better way to write it is, you know, SI minus A inverse is going to be equal to the SI minus A bar inverse. So eventually what it means is determinant of SI minus A is equals to the determinant of SI minus A bar. Right, so from here you can say that SI minus A will be S plus 15 minus 8, 15, S minus 7, and this is equals to the determinant of S minus 1, A0, S plus A1. Okay, so the determinant is simply S plus 15 times S minus 7 plus 8 times 15. And here it's going to be S plus A1 plus A0. Right, so here on the left, we will have S squared plus 8S plus 15, and it's going to be S squared plus A1S plus A0, right? So by comparison, you can see that A1 is 8 and A0 is 15. So I mean, the A bar or the controller canonical form will be simply 0, 1, minus 15, minus 8, and the B bar is 0 and 1. Okay, so that's your controller canonical form. And remember, we started here from, we went to the transfer function first, and then we went to the state space. All right, so the question now is, or the next question we have in this line of line of topics is how do we transform one state space to the controller canonical form, right, using a similarity transformation. So how to convert a state space to controller and controller canonical form using a similarity transformation. Okay. So, I mean, I will not give you the whole derivation here. We can always start from the first principles and start to derive that transformation matrix T. But I can give you the simple relationship. So given a given a state space model X dot AX plus BU and Y CX plus BU. We can use the following similarity transformation. to convert it into a controller canonical form, and that special transformation T is actually the controllability matrix of AB times the controllability. So controllability matrix of A bar and B bar times the controllability matrix of AB inverse. Okay, so it's I mean, I can write it for you where the C A bar B bar is actually B bar and A bar B bar, right? So you know, the B bar is just all zeros, and then the last entry is 1, and the A is the last row is the special one. The rest is you know, it has a special structure. So if you multiply A bar and B bar, you're actually picking up the last entry of the first column. So essentially, you know, this is going to be a zeros, and the last entry is a 1, right? And if you multiply this, then everything is 0 except the last one, which is minus A0. So that's a structure, right? So you only have to know A0, you just negate it, and you got your controllability a matrix, right? But obviously this here is in a 2x2 case, so I am not going to you know, generalize this. So in a general case, it's going to be general case is going to be A bar squared, B bar, and so on, right? And similarly, you can compute those, but the main thing is you need to have that controllability matrix. So I'm going to solve this example for you to help you better understand. It's the same example as before. So instead of going through all that process, we will do it in the similarity transformation way. So let's say we want to transform A minus 15 minus 15, 8, 7, and B is 1, 1 to controller canonical form. So we've got the transformation, but let's compute it. So so to get A0, basically your in this 2x2 case, your the C A bar B bar is going to be, so pretty simple, right? So B bar is 0, 1, and this is 0 minus A0. So to get A0, we use the characteristic polynomial, which is determinant of Si minus A, right? So determinant of Si minus A is actually the determinant of S plus 15 minus 8, 15, S minus 7, and it's going to be S plus 15, S minus 7 plus 8 times 15. So it turns out to be S squared plus 8S plus 15. Remember the last element, the entry here is A0, and then this is A1, right? So we can directly see that your C A bar B bar is the augmentation of B and A bar B bar, which we said is 0, 1, 0, minus A0. So it's going to be, oh, it's actually A1, sorry. Is it A1? So let's see what it is. So A bar is 0 minus A0, 0, 1, and A minus A1. B bar is 0, 1. So if you multiply those, you will get A bar B bar to be 0. There's a 1 here. Oh, so the first one is 0, 1, which is just B bar. And then you will have a 1 here and minus A1, right? So it's let me just correct this. So it's not a, it's A1 here. And A1 is from the characteristic polynomial is 8. So, and this was a 1 here. So what you get is 0, 1, 1, minus 8. That is your controllability of A bar and B bar. And from the previous example, the C of AB, we've already computed it before in the previous time. So it's 1, 1, minus 7, minus 8. So your T, so transformation, T is going to be, if you write it directly, it's going to be the C A bar B bar times C of AB inverse. So it turns out to be 0, 1, 1 minus 8 times 1 minus 7, 1 minus 8 inverse. Okay, so if you take the inverse, it's going to be 8 -7, 1, -1. And eventually you get your transformation to be 1, -1, 0, and 1. Right, all these you can do with a computer much easily, but here, just to give you a small example, we're trying to show that actually there exist transformations and you can go from one state space model to the other. So we can check whether this transforms. So A bar is actually TA T inverse. So let's try to do it. The T that we just computed is 1, -1, 0, 1, -15, -15, 8, 7, 1, 1, 0, 0, 1, 1, 0, 1. This is T inverse. So if you multiply it together, you will get the matrix A as 0, 1, -15, -8. And the B bar is T times B. So T is 1, -1, 0, 1 times the B. B was 1, 1. So what you eventually get is 0, 1. So these are your controller canonical form. So what the whole point of doing this is to tell you that there exists a transformation T, and probably we should highlight it here. This is the key here. So if you have any system which is controllable, you can convert it into a controller canonical form from any state space representation using this transformation T, which involves two types of controller matrices and then using it to transform your system. All right, so we have seen controller canonical form and we've seen controllability test. Now what we're going to look at is something called controllable decomposition. So as the name suggests, the idea here is if the system is not completely controllable, can we actually decompose it into a controllable part and an uncontrollable part? That's the whole point. And that's important because when you want to design your controllers, you want to ensure that you are doing it for a system which is controllable. So, a decomposition will help you only take the controllable part into account when you design controllers, and hopefully they will follow your controller. Right, the uncontrollable state is beyond your boundaries, so you can't really do much there. Okay, so as I said, if an LTI system is not completely controllable, then it can be decomposed into a controllable part and an uncontrollable part. Okay, so in other words, when we say that the system is not controllable, we mean that the rank is not full rank, right? So the matrix, the controllability matrix is not full rank, right? So in other words, I will say if the rank of the controllability matrix, which is CAB, which is by definition B and AB, and, you know, all the way up to A n minus 1B, it is less than n, then there exists a transformation there exists a similarity transformation, x bar equals to tx, a bar is t inverse, right? So it's our standard results. And b bar equals to t times b, where this a bar will now look in a special way. So this a bar is going to have 4 parts. Right, so if you look at it in a decomposed way, you will have 4 parts. One is this a bar controllable. Then you have a zero submatrix here, and you will have a bar uncontrollable, and you will have some a here, which is called A12. Right, and the boundaries really depend on how many states are controllable and how many are not, right? I mean, I'll get to this in a minute, but and we'll do an example here also. So this first part, really right here, is the controllable part, right? And this is the uncontrollable part. And similarly, the matrix B bar will also have 2 parts. One is so there will always be a 0 here. So it's not it's not necessarily a single 0, but it may be a vector or a matrix, depending on the type of system, whether it's a MIMO system or and also how many states are controllable and uncontrollable. So this part is the B bar controllable. Okay, so I'm going to also the dimensions. So it's just a remark that the dimensions of A bar controllable and B bar controllable depend on how many states of the system are controllable. Okay. So for example, remember, and actually this is determined from the rank. So in a 3-state system, if the rank is 2, then what you can say is that 2 of the states are controllable, 1 is uncontrollable, right? But in a 4x4 system, let's say there are 4 states and the rank is still 2, then means that there are 2 controllable states and 2 are uncontrollable states. So this boundary really depends on you know, where to draw this. Essentially depends on how many states are controllable or not. So what we said here is that there exists a transformation, but what the transformation is a little non-trivial. So just pay attention. The transformation that will do this trick, matrix T, is constructed as follows. So the T will be a augmented matrix Q1, Q2, Q3, and all the way to well, I mean, Q1, Q2, all the way to Qn, and let's call it N1, and the last one is a Qn, and we take the inverse here. So what are these vectors Q? So these are linearly independent columns of the controllability matrix, right? And this Qn is a arbitrary, so you can choose it arbitrarily to make T invertible. Okay, so one thing is very clear, that if you were to choose it arbitrarily, then the transformation matrix is not unique, right? Everybody can have its different transformation matrix. And also the other thing is that if you choose a different transformation matrix, then your A bar controllable and A bar uncontrollable, and that decomposition may also not be unique. But again, that is not a problem, because you can always do some standardization later on. You can always convert to canonical forms. But the whole point is whether the system is separable or not into controllable and uncontrollable parts. Okay, so I'm going to write an example here, and that should help you understand how to do this. So finally, I think if you use this transformation matrix and you end up with an A bar and a B bar in this form, which has different pieces, your final controllable system will be written as, so the controllable will be a, let's call it X bar controllable dot is A bar controllable X controllable bar plus B controllable bar U, and then Y is C bar controllable X controllable bar plus DU. right? So once you have that matrix T, then I think you can directly obtain the A, B, C, and D and form a reduced system. So let's get started with a example. Actually, I will try to reuse the previous example here. Something that we have seen already. So if you have a system x1 dot, x2 dot, x3 dot is equals 0, 1, 0, 0, 0, 1, minus 6, minus 11, minus 6 times x1, x2, x3 plus 0, 1, minus 3 u. Then question is, can we convert this into a so find a controllable or so what we call it is a controllable decomposition. Okay, so first thing is remember that we already saw that this system is not, it has rank 2. So if you take, I mean, not this system, but that the CAB, right? Rank is not for the matrix A, but CAB has rank 2. So not completely controllable. Right? So 2 was actually less than 3. So not completely controllable. But one other information we see here is that 2 states are controllable while 1 state is uncontrollable. Okay, so remember, if you want to do a controller or controllable decomposition, then we have to use this transformation. So I'm going to bring up a I mean this formulation. So therefore, to convert this or to obtain a controllable decomposition, we need to use a similarity transformation. So T and T will be what? Q1, Q. I mean we can call it Q1, and then Q2, and then the last one is a Q which is arbitrary, right? Because if 2 states are controllable, so Q1 and Q2 are probably just coming from the controllability matrix. So it is independent columns of CAB. Right, and this Q3 is a arbitrary vector. To make T invertible. Okay. So let's go to the CAB. I mean, I can write it again. So recall for the system, the CAB is, let's go and look at it one more time. The 3x3 example. I guess this is the example. Yeah. So here is the, let's just copy it. So here was the controller controllability matrix. So we can pick any two vectors from this controllability matrix, right? So, I mean, in this case, I'm just going to pick this as Q1, right, and this as Q2. And the reason is because two vectors are, or two of them are independent, right? The other is dependent. That's the meaning of rank 2. So let's pick independent columns here, and the third one can be any arbitrary number, an arbitrary vector. So therefore, we select T as 0, 1, -3, 1, -3, 7, and and we have arbitrary 0, 0, 1. Okay. So I don't know. Let me see if I can do the inverse right now. I'm sure the inverse is going to be a messy number, a messy matrix. I'll still try to see if I can do. So anyway, this is our matrix T. If we use this, and the resulting system after the transformation will be in a controllable decomposition form. So let's use this, and so the transformed system can be written as A bar is a T times A times T inverse. So just give me a moment. I will try to compute the inverse here. Obviously, it's easier to do with a computer. Yeah, so luckily it's not that messy. Turns out to be 3, 1, 0, 1, 0, 0, and 2, 3, 1. Okay, that's your transformation matrix. So the transform system can be T times A times T inverse. So the T is 3, 1, 0, 1, 0, 0, 2, 3, 1, matrix A, going back to the system is, let me just input that into the computer as well. So it's -6, -11, and -6. Right, so 0, 0, 0, 1, 0. And then we have 0, 0, 1, -6, -11, -6. And then we have T inverse. So T inverse is clear. 0, 1, 0, 1, -3, 0, -3, 7, 1. So let's see what the result is. I can verify with the computer, and I get the A bar to be 0, -2, 1, 1, -3, 0, 0, 0, -3. Okay, and B bar is TB, right? It's going to be 3, 1, 0, 1, 0, 0, 2, 3, 1 times B. So B originally was 0, 1, -3. So what we get here is 1, 0, 0. Right, so now question is, obviously you can do the C and D as well, right? So C, if you want, is T inverse C. If I'm right. Is it T inverse C or C times T inverse? It should be C times T inverse. Right, and let's see whether we had a C or not. Yeah, I mean, in this example, we don't have C, but in general, if you had the C also, you can compute the C times T inverse to get your decomposed system. So now the question is, where do we draw the line? Right, remember we said that this is decomposing the system into a controllable part and an uncontrollable part. So where do we draw the line? The easy way to think about it is because you have two states which are controllable. That comes from the rank 2. Right, so the rank 2 tells you that after 2 vectors and 2 rows, you just draw the line. Here as well. So that means this part is telling you that this is a controllable part. Oops. Somehow got rid of the. So this part is really your A bar controllable. And this part is A bar uncontrollable. And this part is A bar 1, 2. And this is a 0 vector. Right, remember we saw the general form of a controllable decomposition is the following. So we see all the elements now. And they'll be controllable. You look at it here, this is your B bar controllable, and this last element is 0. So if I were to ask you, what is the controllable system, you can actually directly see it from here. So let me write it explicitly. The controllable decomposition results in the following. So it's x bar controllable dot is a bar controllable, x bar controllable plus b bar controllable u, and then x bar dot uncontrollable is going to be a bar uncontrollable x uncontrollable. And there's no u after this because obviously it's not controllable, right? So where x bar is x controllable bar, x controllable, not controllable bar, right? So this, so that means that the state splits up into x bar controllable and x bar uncontrollable, and each has its own dynamics. So in this example, you know, we can actually directly see the results. In this example, the x bar controllable is 0 minus 2, 1 minus 3, x bar controllable plus 1 0 1 0 u, right? And x uncontrollable has its own dynamics, right? So it's a one state system. So we're looking at only the a bar uncontrollable, and that's minus 3, right? X bar uncontrollable, and there is no u there. So so why is this important? So remember, we the whole objective is to design controllers, and we want to have certain properties that controllers have. For example, stability. We want to track a certain reference. So we want to control our system from one state to the other. So as long as the uncontrollable part does not blow up, or it's you know, it is stable, which in this case it is, because they you know, I can see it from here that the eigenvalue or eigenvalue of matrix A is -3. So I can see that this uncontrollable part is stable. So all we have to worry about is the controllable part. Okay, so as long as the uncontrollable part doesn't blow up, your system still has some level of control that you can exert on it. So that's a property that, you know, that is very helpful, and we can make use of it in design problems. And hardly, you know, in real systems, you will have states that are completely controllable. So decompositions into controllable and uncontrollable parts is important. And I mean, let's say in this problem, if I ask you whether the system is controllable or completely controllable, the answer is no. The system is not completely controllable. So you decomposed it and gave me two subsystems, and you told me one of them is the controllable part and the other is the uncontrollable part. Okay, fair enough. So next question is the controllable part stable? So controllable part is the top one. Right, I mean, I can just write these so is the uncontrollable subsystem stable, and well, let's write it as the controllable subsystem, and this is the uncontrollable subsystem. So question is the uncontrollable subsystem stable? And I just told you the answer. Yes, because the uncontrollable subsystem has a pole at -3, right? Which is in the left half plane. Okay. Now, if I ask the same question, I need answers from the audience now. So is the controllable subsystem stable? So let's see what you guys can come up with. So I need your help now. Can somebody volunteer to answer this question? And by the way, these are exactly the type of questions that can be on a quiz. So it shouldn't be very surprising. I mean, if I ask you if a system is stable or not, I think we had a very detailed discussion on it in a previous lecture about left half planes and about unit circles and where the poles have to be and what is the reason for that.
Would it be
So
unstable?
So you're saying stable?
Unstable.
It is unstable. So what is the reason for that? I mean, it's not guesswork. It has to have some method to the madness. So why do you think it is unstable?
Looking, I'm basing this off the previous
So can you tell me
if we're looking at the what are you saying, Professor?
Yeah, I'm saying what is the controllable subsystem?
That would be matrix 1-0.
No, I'm talking about the system, right? Controllable subsystem is this whole piece, right?
Mhm.
I mean, this is the uncontrollable subsystem, this is the controllable subsystem. So I'm asking whether each of them is stable or not. So I looked at this system and I directly can say it is stable because it is written in the form of x dot equals to ax, right? And a here is simply the number -3. So it's a 1-by-1 system. So eigenvalue is the matrix itself. So because it is -3, I know that it's in the left half plane. So e to the power -3 is going to die out over time. So this is a stable subsystem. But now the question comes, same question I have to ask for this subsystem. Is it a stable system or not? So I'm going to reiterate our previous discussion. Remember, I said the solution of the system is going to be e to the power -at x0 plus so many other things. Right, so e to the -at shouldn't blow up. So the eigenvalues of a should be negative. So it's e to the at. So all eigenvalues of a should have negative real parts. Right, otherwise the system is going to blow up, right? It's not going to be stable. So if I apply that logic here, I need to look at the eigenvalues of this matrix. So look at eigenvalues, because eigenvalues are the poles of the system. 0, -2, 1, -3. So eigenvalues are, I mean, here I just opened my MATLAB and searched. So they are 0.5616 and -3.5616. So now can somebody tell me whether it's stable or not?
It's unstable because of the positive pole.
Yes, correct. So, I mean, it's a simple idea. So system is not stable because one of the poles is in the right half plane. Okay, so eventually if you do e to the negative or e to the at, then one of the term will be e to the power 0.5616t. And if you plot it over time, you know, it's going to keep increasing. So that's an indication of instability. We don't want things like this to happen. We want things to decay over time, go to 0. So all the poles should have negative real parts. That's the de facto standard. Okay. So all right, I think we have covered what we wanted to talk about today, and I would want to know if you have questions so we can talk about them. So is it clear whatever we are talking about? Or are you kind of getting the idea? Or is it too difficult? Or I mean, any comment?
Professor, could you please go through how you obtained the eigenvalues for 0.5616 and -3.5616?
Yeah, okay. So, I mean, right now I just used MATLAB function to compute the eigenvalue. But in general, I mean, I can just write a note here, right? So to compute eigenvalues of a matrix A, we need to solve for AX equals to lambda x, right? So lambda is the eigenvalue and x is the eigenvector. So it's a linear system solution problem, right? So for example, if A is just A is 1 by 1 matrix, for example, right? In this case, or in this example, your A is -3. So -3x equals to lambda x, right? So for any x, lambda equals to -3. So the eigenvalue is -3. But imagine you have a different matrix. So for example, you have matrix A is 1, 2, 3, 4. Then you want to solve for AX equals to lambda x, which means that for any x1, x2, if you multiply it by the matrix A, you will get a multiple of that vector. So here in this case, you will have x1 plus 2x2 equals to lambda x1, and then 3x1 plus 2 or plus 4x2 equals to lambda x2, right? So you try to solve for lambda here for any x, right? In other words, you do A minus lambda I x equals to 0. So you just have to solve this equation. Do you get my point here? So it's going to be x1, actually 1 minus so it's 3 minus lambda x2, 3x1 plus 4 minus lambda x2 equals to 0. So you just solve for x1, x2, and see what is the lambda that will be the solution of this. So you solve for x1, x2, and lambda, right? So you have two unknowns, you have three unknowns and two equations. So you might get.
So Professor, is it because the lambda value would end up being positive that would make that controllable part unstable?
Yes. So just because the thing here, that's the reason of the instability, right? And this is coming from the solution of LTI systems. If you remember not last time, maybe second lecture, I think I told you the solution x of t is two parts basically. One of them is e to the power at x0, right? And then the other one is an integral based on u of tau d tau. So this is like the forced response. This is the natural response. Now, if the eigenvalue of A is positive, then this thing is going to grow over time. As time goes to infinity, this e to the power plus something T is going to grow. So that leads to an instability. So you always have to make sure that your eigenvalue of A is in the left half plane or negative. So then your natural response will, decay over time and go to 0. So at least there is no instability because of this. Okay, so somebody who was asking about eigenvalue and eigenvector, it's a linear algebra question, but I mean, you can always use MATLAB to compute it. So for this course, I mean, there is no exam, so you wouldn't have to do it anywhere. But for homeworks or a quiz, I mean, it's not expected to know the eigenvalues, but obviously, if you want, you can use MATLAB or something. So the MATLAB function for this is the EIG of the matrix A. That's going to give you the eigenvalues. Okay, any other comments or concerns? So today we will upload the homework, second homework. And by the way, the quiz is also due soon. So you had one quiz and one homework already. So for next week, we will have homework, which will be uploaded and will be due next week. And the projects hopefully are formed. I will go through them and if there is some feedback which is important for you to know, I will get back to you. I mean, if I don't, then I think it's by default, you should assume that you can keep working on it. So the best thing is probably in the break, which is going to be after a couple of weeks, in the spring break, I think try to focus on your projects and try to work on them as much as possible, so you're not falling behind at the end. So some people have reached out for help, and I'm working with them regarding projects. But I mean, let me know if you have something to talk about. Okay. Anything else before we wrap up our lecture? Okay, if not, then I'll see you next week. So stay warm and have a happy and a great week ahead.
Thank you, Professor.
Okay,
Thank
bye-bye.
you, Professor.
Professor.
All right, bye-bye.